All right, let's look at the momentum and impulse review. Number one, impulse of an object is equal to the change in momentum of an object. So a change in momentum occurs when there's a change in velocity, final velocity minus initial velocity, like we've seen in our equation. And when that occurs, momentum changes, and we call that change in momentum impulse. Number two, to decrease momentum. So I want to decrease momentum, and I know there's a direct relationship between momentum and mass and momentum and velocity. So if I want to decrease momentum, then I must also decrease mass, because whatever one does, the other one does, and I also need to decrease velocity. So by decreasing either one of those, I am going to decrease the momentum. There's a direct relationship. Number three, which of the following is the appropriate units for momentum? Well, if you think about it, your equation is mass times velocity. So the units for mass are kilograms, and the units for velocity are meters per second. And in my equation, mass is being multiplied by velocity, so my units are kilograms times meters per second. Number four, chest bump is a good example of which type of collision. So chest bump, two players are running, they're jumping up in the air, hitting chest to chest, and they are coming back down, they are separating. So anytime there is a collision where a separation occurs, like a chest bump or a fist bump or a bowling ball hitting pins, that is an example of an elastic collision. Catching a ball is a good example of which type of collision. So catching a ball is two objects colliding and staying together or sticking together. So catching a ball is a good type of collision. Throwing a dart at a dartboard is a good type of this, or a good example of this type of collision. This is an inelastic collision. Two objects collide and stick or stay together. That's inelastic. Number six, complete the sentence. The law of conservation of momentum states that, so we're talking about conserving momentum. And that word conserve means to save. So it means that momentum is staying the same. It's being saved. So to complete the sentence, it says the law of conservation of momentum states that individual pieces may change, but the overall or the total momentum stays constant. So the individual pieces, meaning the masses could change, the velocities could change, but because momentum is being conserved, the total overall momentum remains constant. Meaning it doesn't change, it is conserved. Number seven, in order to catch a ball, a baseball player moves his or her hand backwards in the direction of the ball's motion. This reduces the force of impact on the player's hand. So remember, we've talked about force and time. We said that impulse was equal to force times time. So because force and time are being multiplied by each other, there's an inverse or indirect relationship. So if the force is reduced, meaning the force goes down, then that means that time has to increase. Well, if you are moving your hand backwards in the direction of the ball's motion, it's reducing the force. So if my force goes down, that means my time has to go up. So in other words, the time it takes to stop the ball increases, in turn reducing the amount of force. So you can just say the time taken to stop the ball is increased. So in other words, if we are in a car and an airbag is deployed, the airbag is going to reduce the amount of time it takes for your body to come to a stop, Therefore, it's going to reduce the force that is acting on your body in return. So the time it takes to stop the ball is increased. The airbag, the time it takes your body to stop is increased, and in return, it reduces the amount of force acting on you. Number 8, inertia or in motion, or mass in motion. Well, momentum is mass times velocity, so it's mass times motion. We call that inertia. So momentum is basically inertia in motion. Number 9, a 0.5 kilogram T-ball is hit from rest to a speed of 60 meters per second towards an opponent. What is the impulse exerted on the ball? Okay, so in this problem, I've got mass, I've got an initial velocity of 0 because it's at rest, and I've got a final velocity of 60. I want to know impulse, which is J. So of my two impulse equations, I'm looking for the impulse equation that has mass, initial velocity, and final velocity. And that equation says impulse equals mass times final velocity minus initial velocity, where J is equal to 0.5 times 60 minus 0. So 60 minus 0 is 0, and 60 minus 0 is 60, times 0.5 gives me an impulse of 30 newtons times seconds. Okay, looking at number 10. I've got a can crusher that at a recycling plant that applies 45 newtons of force over 0.30 seconds. I want to know what the impulse is exerted on that can by the crusher. So I'm looking at a force here. I'm looking at time, and I want to solve for J. So if I'm solving for J and I've got force and time, my impulse equation is force times time. So if I have a force of 45 and a time of 0.30, when I multiply those two together, I get 13.5 newtons times seconds. All right, number 11. So what is the speed of a 3 kilogram object whose momentum is 6 kilograms times meters per second? So I have kilograms, which measures mass. I've got momentum, which is P. I want to know velocity, the speed. So I'm going to use my momentum equation, mass times velocity. If the momentum is 6 and I have a mass of 3, a velocity that's unknown, to get V by itself, I need to do the opposite of multiply by 3, and that is to divide by 3 on both sides. So the 3's cancel here, and I'm left with 6 divided by 3, which is 2 meters per second. Number 12, I have a stationary 0.15 kilogram soccer ball. It's kicked with a force that lasts for 0.10 seconds. The ball shoots across the field with a speed of 20 meters per second, scoring a goal for the team. What was the force of the ball was kicked? So I'm solving for F. I want to know the force. The soccer ball has a mass of 0.15 kilograms. It lasts for a time of 0.10 seconds with a velocity of 20 meters per second. This is my final velocity, and I know that because it tells me the ball was stationary, which is the initial velocity. So if I'm trying to solve for force and I've got final velocity, initial velocity, mass, and time, I'm going to use my equation Ft equals m times Vf minus Vi. And if I substitute in here, force is unknown, my time is 0.10, mass is 0.15, final velocity is 20, initial velocity is 0. So 20 minus 0 gives me 20. And if I multiply that by 0.15, I get 3. So on the left, I have F times 0.10 equals 3. To get F by itself, I need to divide both sides by 0.10. And when I do that, my 0.10s on the left cancel out, which leaves F all by itself. And my force is 30 newtons. Number 13, I'm referring to the box. It's got a mass of 2.20. It's moving 4.5 meters per second to the right. It's got a lump of wet sticky clay thrown directly against it. The clay is moving directly to the left at 6.8 meters per second and has a mass of 0.25. So I've got masses and velocities. Let's say this is M1, this is V1, this is M2, and this is V2. Now, because it is moving to the left, that makes this velocity a negative 6.8. And in 13, I want to find the total momentum before they are stuck together. So I don't need to actually solve this through. However, they are two objects combining to form one, so it's an inelastic collision. So the first part of it looks like this: M1 V1 plus M2 V2 equals a combined mass M1 plus M2 times final velocity. Well, if I only want to know the momentum before they're stuck together, then I really don't need to know anything that is on the right side of this equal sign. So I can get rid of that and just look at the left side. So let's plug in everything that we know. I know that the mass of the box was 2.20 and it's moving at a velocity of 4.5 plus M2, the mass of the clay, was 0.25 times a velocity of a negative 6.8. Okay? When I multiply the mass and velocity of the box, I get a momentum of 9.9. And when I multiply the mass and velocity of the clay, I get a momentum of a negative 1.7. And all I need to do now is add a positive 9.9 with a negative 1.7, and that gives me a total of 8.2 kilograms times meters per second. On the back, number 14, I've got a collision between two carts showing me before and after. I want to know what type of collision is seen above. Well, I see two carts that are going to come together, and afterwards they're separated. So when two carts collide and separate, that is an elastic collision. Number 15, I want to know the momentum of the 1 kilogram cart before impact. And number 16, I want to know the velocity of the 2 kilogram cart after impact. Okay, so let's start by solving for the momentum of each cart. I know that momentum is mass times velocity. So if I want to find the momentum of the first cart, I take that cart's mass, which is 1, multiply it by its velocity, which is 3, and I get a momentum of 3. This cart over here to the right, it's got a mass of 2, and it's got a velocity of 2. However, the velocity is pointing to the left. The arrow here indicates it's a leftward movement, which means that my velocity is now a negative. So it's a positive 2 times a negative 2, which gives me a negative 4. Now if I want to find the total momentum, I take a positive 3 and I add a negative 4. And 3 plus a negative 4 gives me a negative 1. So my total momentum is a negative 1. Which means the total momentum after the collision also has to be negative 1. So mass times velocity of this first cart after the collision. Positive 1 times 2 meters per second, also to the left. That is a negative direction. So 1 times a negative 2 is a negative 2. And if my total momentum is a negative 1, my momentum of the first cart here on the left is a negative 2. If I want to find out the momentum of this cart, I can take let's do it on the right, negative 1 and subtract a negative 2. So the two negatives cancel each other out, and you end up with a negative 1 plus 2, which is a positive 1. So mass times velocity, I've got a momentum of 1, a mass of 2. I want to solve for velocity. So P equals mv. If I've got a momentum of 1, a mass of 2, I want to solve for velocity. I divide 2 to the other side. These 2's cancel, and I've got 1 over 2 equals v, which is simply 0.5. So the momentum of the 1 kilogram cart before impact. So before impact, here's my 1 kilogram cart. Its momentum was 3. If I want to look at the velocity of the 2 kilogram cart after impact, here's after impact, 2 kilogram cart, the velocity we just solved for it was 0.5 meters per second. Okay, number 17, I've got a bowling ball traveling 2 meters per second to the right, while a 0.5 kilogram basketball rolls 10 meters per second to the left. After hitting each other, the basketball travels 5 meters per second to the right. What is the velocity of the bowling ball after the collision? So you have a bowling ball and a basketball colliding. They will separate each other from each other, so that is an elastic collision. Okay. So I've got two objects in comparison. The 4 kilogram bowling ball, this is going to be M1. It's moving 2 meters per second to the right. That is V1. The basketball, that's my second mass. That's M2. And it's moving 10 meters per second to the left. So this is V2. However, it is going to be negative. Okay. Now, after it hits, the basketball travels 5 meters per second to the right. So this is V2 after. What is the velocity of the bowling ball after the collision? This is going to be V1. So let's see. Before, I've got M1 V1 plus M2 V2 equals, and then after, I've got M1 V1 plus M2 V2. So let's substitute everything that we know. I've got a mass. The bowling ball has a mass of 4 and a velocity of 2 to the right, plus the basketball has a mass of 0.5 and it's traveling 10 meters per second to the left, so that's a negative 10, equals. Now, after the collision, their masses do not change, so it's a 4 kilograms for the bowling ball. The velocity of the bowling ball afterwards, that's what we need to solve for, so that's V1. Plus the mass of the basketball, that's 0.5, and its velocity is 5 meters per second to the right. All right, so let's work this out from left to right. 4 times 2 is 8, plus 0.5 times a negative 10, that is a negative 5. equals 4 times v1, that's 4v1, plus 0.5 times 5, that is 2.5. Okay, so 8 plus a negative 5 is 3. I have 4v1 plus 2.5. If I have a plus 2.5 hanging out there and I want to move it to the other side, I do the opposite, and that is minus 2.5 on both sides. So the 2.5s here cancel. I've got 3 minus 2.5, which is simply just 0.5. Equals 4v1. And to get v1 by itself, I need to divide by 4, because I need to do the opposite. And these 4's cancel, and I've got 0.5 divided by 4, which is 0.125 meters per second. That is the velocity of the bowling ball after it collides with the basketball. And the last 3, I'm talking about the bug colliding with the windshield. Now the bug has a small mass compared to the bus, which has a large mass, but number 18 is asking about forces. So the bug is hitting the windshield of the bus with a force that is equal to the force of the bus hitting the bug. So their forces compare in a similar manner, meaning that their forces are the same. Okay, so Newton's third law says that forces are equal in magnitude, opposite in direction. Number 19 is talking about the time of impact. So the bug is hitting the windshield is hitting the bug. They are colliding with each other and exerting forces on each other in the same amount of time. So their time here is the exact same. And the last one, number 20, says, how does the impulse compare? So I'm looking at impulse. And impulse is force times time. Well, if the forces on impact are the same and the time of impact is also the same, then the impulse for each of them is also the same. The only thing that's different here, other than the mass, is the acceleration. So objects with small mass, like the bug, are going to have a lot of acceleration. Objects with large mass, like the bus, are going to have very little acceleration. But the forces exerting on each other will be the same in magnitude, opposite in direction. The impact time will be exactly the same, and the impulse will also be the same.